Now let's move on to another related topic, shift registers. Here's the basic circuit. It comprises a set of flip-flops, with the output of each flip-flop connected to the input of the next one in the sequence. All the flip-flops are connected to the same clock input. So when a clock pulse occurs, they'll all load a bit of data simultaneously. Thus, flip-flop 0, the leftmost flip-flop, will load a bit of data from the data input on the left. And each following flip-flop will load a bit of data from its predecessor. The fact that the flip-flops are physical circuits means that their output takes a little time to update after the clock edge that loaded them, so the value that each flip-flop picks up from the previous one is the old value, not the new value that it's just loaded. In other words, the data value that's been input from the left does not race from left to right through the whole set of flip-flops, but progresses sedately one flip-flop at a time each time a clock edge occurs. And because each flip-flop's output is available continuously, the value of the 4-bit word that the shift register contains can be read at any time. Shift registers have a number of uses. One of the most common is converting serial data to parallel data. That is, converting data that arrives a bit at a time into a multi-bit word that can be transferred from place to place in a single operation. For example, an 8-bit shift register could be clocked 8 times to load 8 bits of data, and then the value that it contained could be loaded in one clock cycle into an 8-bit wide memory. This type of operation would typically occur when data that arrived at a computer along a serial communications link was converted into 8-bit bytes that were stored in sequential memory locations. Another less common use for a shift register is to perform a fast division by 2. In this case, we'd load the bits of the number into the shift register in parallel. I haven't shown you a circuit that can do this yet, but by now you should be able to modify the basic shift register circuit to do it for yourself. So we load a word of data into all 4 flip-flops of the register in parallel, shift the data right 1 bit using the standard shift register behavior, ensuring that something sensible is input into the data input in the left, and we've divided our original number, which was 5, by 2, producing a quotient of 2 and a remainder of 1. Whether we store the remainder in another flip-flop or throw it away depends on the situation in which the divide by 2 circuit is used. And not surprisingly, a multiply by 2 circuit works just the other way round. We load a number into the shift register, shift it 1 bit to the left this time, ensuring that a 0 gets input into the least significant bit, and hey presto, we've multiplied our number by 2. If a 1 gets shifted out the left-hand end, then an overflow has occurred. Whether this is an error or not depends on the circumstances in which the multiplication circuit is being used. If we want to multiply by 4 or 8, you could use the same circuit, but after you'd loaded the number, you'd shift it left 2 or 3 bits respectively. Let's look at a commercial shift register. It's a little more powerful than the circuit I've shown you. It can parallel load data, and it can shift data to the right, but not to the left. As with many devices, we can divide the inputs into 2 groups, control inputs and data inputs. There are 2 clocks, one to initiate a parallel load and the other to initiate a shift right. There's also a control input called S, which specifies which operation will be performed, a shift or a parallel load. Don't confuse S and the clocks. S specifies which operation the chip will perform. The clocks specify when the operation will occur. If S is low, a falling edge on clock input 1 effects a shift. If S is high, a falling edge on clock input 2 effects a load. Then there are the data inputs. Just like the basic circuit, this one has a single serial data input, but there are also 4 additional inputs for parallel loading. And finally, there are 4 outputs, one from each flip-flop. Now let's have a look at the actual circuit. As with the basic device, it has 4 flip-flops. It also has some control inputs. The first one is called S, and it's the select input that specifies which operation to perform, shift or load. We sometimes need to know when S is high and sometimes when it's low, so it's convenient to have both S and its inverse available. And the clocks are active low, so we'll invert them so we have a straightforward active high clock inside the device at least. Now, when should we clock the flip-flops to load them? If S is high, then clock input 2 should cause a load to occur. Alternatively, if S is low, then clock pulse 1 is in charge. So that gets the flip-flops loaded at the right time. But now we have to provide them with the right data from either the single data serial input or the set of 4 parallel data inputs. Well, we know that serial data is to be input if S is low. So let's AND the serial data with the inverse of S. Alternatively, if S is high, parallel data is to be loaded. So let's AND the parallel data with S and present that as the other source of data. This is a little more subtle than it might first appear. If the selected data input is 1, then a 1 gets through the OR gate to the flip-flop. That's straightforward enough. But if the selected data input is 0, then both data sources are presenting a 0 to the OR gate. The selected input, because its data value is 0, and the other one, because the select signal closes down the path through the AND gate, whether the data value is a 0 or a 1. This type of circuit that delivers one data value from a set is called a steering circuit. The same problem, whether to select serial or parallel data, recurs for each flip-flop. So the same steering circuit is repeated for each flip-flop. And of course, there's no point in the circuit if we can't get any data out, so let's connect up some wires to the outputs of the flip-flops.